Hello, thanks for tuning back in. This is the next video in the differentiation rules series, derivative applications part 2. For this particular video, we're going to go over an example where we have a business or economics type of a problem. And so we'll go through it, show you how we can actually use derivatives to solve some of these type problems. So our problem says, according to economic theory, the demand, which we're labeling X here, for a quantity in the free market decreases as price increases. Of course, we all know this. Of course, if the price increases for something, we tend to want to pay for that. But of course, as it decreases, meaning a sale, then of course, more people want to buy it. So that's what that's basically saying there. So we suppose that the number of headphones that people are willing to buy per week from a retail chain at a price of P dollars will be given by this particular function. So we're saying price is a function of, demand is a function of price. And so here's our function, nice rational function. And this particular model for demand based upon price is good for from $10 to $70. And so here's kind of what the curve looks like. And we're asked to do the following. First, find the derivative of demand with respect to price, okay? And so basically what we're trying to find out is track the rate of change of demand as it relates to price. And then after we're done with that, then we'll find the demand and the instantaneous rate of change of the demand with respect to price when the price is at $30. And then finally, we'll estimate the demand if we increase the price from $30 to $31. So we'll start with this one first. So here, we'll take this and take the derivative of our function. So taking the derivative of this particular function here, we notice that we have something in the numerator, something in the denominator. And to take the derivative of that, we will use the quotient rule, which is low d high minus high d low over low squared. So we'll go ahead and apply that now. So low, and then derivative of high minus high times the derivative of the low function all over the low function squared. Of course, if we look here, we see that the derivative of 5,000 is 0 because the derivative of any constant is 0. So this whole term will basically go to 0. And now we're just left with the minus 5,000. And then the derivative of 0.3p is just 0.3. And the derivative of 1 is 0. So we'll just leave that off. And we're here, and if we take 0.3 of negative 5,000, we will end up with negative 1,500 divided by 0.3p plus 1 quantity squared. And so basically what this derivative is communicating is that demand will follow this particular function here. And you notice that this negative is trying to say that, that the rate of change is pretty much going to be negative for all values of p in consideration here. And if we look, this goes right along with what our graph is trying to communicate with us. From price of 10 to the price of 70, we see that the rate of change, or the way that the function is going, it is decreasing. And thus, the slopes of the tangent lines of each of these points are decreasing as well. And so that leads me into a segue into part B, which says find the demand and the instantaneous rate of change with respect to price when the price is at $30. Okay? So basically what this part of the question is asking for is two things. Is asking us to, first of all, find out what X of 30 is, or demand when the price is at 30. And then it's also asking us to find out what the instantaneous rate of change is for demand at the price 30. So of course for here, all we have to do is just plug in 30 into our original function. And so we see here that 30% of 30, or 0.3 times 30, is just 9. And of course, 9 plus 1 is 10. And 5,000 divided by 10 is 500. So the quantity that our market is going to, try to demand is going to be 500 when the price is at $30. When we're here, we do the rate of change of this particular function at 30. We've already found out what the rate of change is, so all we need to do is just plug in 30 into our derivative, and we'll find out how much our demand is changing right at $30. Okay, so once again, we're here. We know that 30 times 0.3 is going to give us 9. Nine plus 1 is 10. And of course, 10 squared is 100. And so if we divide negative 1500 by 100, we get minus 15. And this would be, the units on this would be headphones per dollar. Okay. So we see from here, demand is 500. And at a demand of 500, the demand is decreasing at a rate of 15 headphones per dollar. Okay. Of course, our last question says, let's estimate the demand if the price increases to $31. And so to do this, I'm going to go here. This is the actual demand at the price $30. And here, that's a sketch of the tangent line. And what we found here is the slope of the tangent line. And what this question is asking us for is if we went from $30 to, let's say, $31, could we use this particular line to estimate what the new price of demand is going to be? Okay. And remember, this is only an estimate. So to do that, we could do the following. We could say that the demand at the price of $31 would be approximately equal to, if we're taking this line into consideration, we would have the slope, which would be this, the slope of this line times the difference in between $30 and $31, which is just $1, plus our known demand at 30. And of course, here we know that this is a quantity of 500. We know this is minus 15. And so if we take negative 15 times 1 and then add 500 to that, we get 485. So our estimate for what the demand would be if we raise the price $1 is that we basically lose a demand of 15. So 15 less people wanting headphones. And so this concludes the example for derivatives, applications, a business economics example.